Okay, so in this edition of the Motivic Geometry Seminar, I'm really happy that Charanya Ravi will tell us about Milner excision for K3 of stacks.
Thank you. Thanks a lot for this invitation. So today I'll talk about Milner excision for K-theory of stacks, and this is based on joint work with Tom Bachmann, Adeel and Vladimir Sosnilo. So first I'll explain the Milner excision for stacks and then use that to show a pro-cdh descent for stacks. And then if time permits, I'll also talk about how to deduce the Kerz-Strunk-Tamme's version of Weibel's conjecture now for stacks using similar ideas. Okay, so first, in general, we would be interested in looking at squares of algebraic stacks of the following form. So consider a Cartesian square, delta of say Noetherian stacks or any stacks of the form y to x, where this map is affine. And then you have some closed embedding sitting inside this and the pullback of this. And the question that in general we would be interested in this part of the talk is when the K-theory sends such a square to a Cartesian square. So when does K-theory satisfy excision for such squares? And such squares have been classically studied in rings, for example, and this is related to the classical theorem of Bas, Milner, and Murthy about Milner square of rings. Let me recall the definition. So a Milner square of rings is a Cartesian and co-Cartesian square of the form. So let me call this delta ring. So this is a square of rings of the form A to A mod I and B to B mod J. And it would be such that the ideal I and J are isomorphic under the given assumptions. And given such a square of rings, it's a classical theorem of Bas, Milner, and Murthy from the 60s. Bas, Milner, Murthy. That for delta ring, there exists a long exact sequence which starts from K1. So K1 of A would map to K1 of A mod I direct from K1 of B. So let me just call this A prime and B prime. And then this goes to K1 of B prime. And there is a boundary map which goes to K0 of A and so on. And it extends all the way to the right to the negative K groups. And from the original question that we are interested in, that if the square, if we take K theory, is a Cartesian. So if it was Cartesian, then we would also have this exact sequence extending to the left. So it would be for also the higher algebraic K groups. And the question is, does such a exact sequence exist? And what this classical theorem tells you is that if you start with K1, then you do have such a sequence. So let me make this notation. So for me, K would always denote the non-connective algebraic K theory spectrum. Non-connective K theory spectrum. So if you're working with schema stacks, you can just take the perfect complexes and then look at this as an infinity category, and then this non-connective K theory spectrum is in the sense of Bloomberg-Edman Taboada, Or just in these geometric settings, you could also take the usual construction where you define the first connective K-theory spectrum and then deloop it. So that would be the notation. So K would always be the non-connective K-theory spectrum. So the question is, can we extend it to the left, this exact sequence? And unfortunately, this is not possible. This was shown by Swan, who showed that there does not exist any K2 functor for which it even extends to K2. So, so this does not extend to the left. Okay. So then what can we do? So it's a recent result of Land-Tamme, who showed that if you work with pro-K theory, then we can extend this whole sequence to an actual Cartesian square of K theory spectrum. So Land-Tamme. So if the square of rings was Tor independent, so if this is Tor independent, that means that the Tor group of A prime and B over A, all the Tor groups vanish. Then if you apply K theory to that square, then K of delta is Cartesian. So basically, you're saying that you have a square of rings, it is Cartesian, but if it is Tor independent, it would also be homotopy Cartesian. And in that case, you do have a K theory sending such a square to a Cartesian square. And if you only have pro-Tor independence, so if delta ring is pro-Tor independent, so by that, I mean the Tor groups which you take Tor I, Tor I A, A mod I par n, B, and take the pro groups corresponding to this. So you take all the thickenings of your ideal and ask that if this vanishes, so if this vanishes for all I greater than 0, then if you take the pro spectra, then K of A to K of A mod I par n to K mod B to K of B mod J par n, this is Cartesian. So basically, K theory is pro-Cartesian on once you assume this pro-Tor independence condition. Okay, and it's a theorem of Morrow that if you work with commutative rings, Noetherian commutative rings, then this pro-Tor independence is actually automatic. So if your original square of rings was square of commutative Noetherian rings, which is Milner, then it would always have a pro-excision for K theory. So remark. First, pro-Tor independence is automatic for Milner squares of automatic for Milner squares of Noetherian commutative rings. And now, if you can combine this pro-excision for rings with the Zariski descent for K theory, this shows that if you have a square of schemes, which is Milner, then it would always give you pro-excision and K theory. So K-theory satisfies pro-excision for Milner squares of Noetherian schemes. So this follows from Land-Tamme plus remark 1 and Zariski descent. Okay, and the kind of key insight of Land-Tamme for the proof of this result was the following. So, so given delta ring, so given a square of rings, which is of the form the Milner square of rings that we started out with, A mod I, A prime, B prime, you can always construct an even ring, which is called the O dot construction. And if you apply K-theory to this kind of refined square, then that is always Cartesian. And what this store independence kind of buys for you is that this O dot construction is pro-equivalent to the B prime. So given delta, there exists a refinement A prime. So this is your original square. And you can always form this A prime B prime such that K-theory sends in a square to a Cartesian square. And under the additional condition, so under tall vanishing condition, so this A mod I par n, A B mod J par n, B, this is pro-equivalent to B prime, so B mod J par n. So, so therefore, this would show basically that if you applied pro-K theory, then it is Cartesian. Okay, so now, now when we want to get back to our original question, where we had a sort of Milner square of stacks, and does that have excision for K theory? So, if we want to prove Milner excision for stacks, so again, we can reduce it to simpler case, just like in the case of schemes, we can reduce it using Zariski descent to just looking at affine schemes. In the case of stacks, we have this local structure theorem due to Alper, Hall, Halpern, Leisner, and Reed, which tells you that under some good enough conditions, your algebraic stacks are basically locally in the Nisnowitch topology, all given by quotient stacks of affine schemes mod linearly reductive. And this is the case that we want to reduce to in this case. So using local structure theorem for stacks. Reduced to the case of some affine mod linearly reductive group scheme. And then we, because we also have Nisnowitch descent for stacks, Nisnowitch descent for stacks due to Hoiva and Krishna. This tells you that you can reduce to basically looking at squares of this form. So, reduce Milner excision for stacks to this quotient stack case. Okay, so now what we're going to do, therefore, is prove this result of Land-Tamme for the equivariant setting. So basically, you're given a square of rings, but now with some linearly reductive group action, and we want to ask if equivariant K-theory or the K-theory of the quotient stack, if that gives you back a Cartesian square or at least a pro-Cartesian square under the given condition. And unfortunately, there's no way of directly adapting this kind of result of Land-Tamme to the equivariant setting. So if you started off with a square, this A prime, B prime, where everything has G actions, and you constructed this kind of O dot construction, there is no natural way of putting a linearly reductive group action or something on the inner this kind of construction such that you can import the whole problem just to the equivariant world. So that's because this O dot construction, the way it is done is it's given by some endomorphism ring of some generator of a category, which fits into this. So you take the square of rings, you replace it by the category of modules over those rings, and this O dot construction is a even ring, which is constructed such that the category of modules over that would give you a excision for K-theory. So there is it's completely categorical, and there is no way of geometrically adapting this. So the idea is that instead you adapt the whole problem into the categorical world. So
just a quick question, Charanya.
Sure.
In the chat, Amalendo asks, what's your base game? Is it a spec of a field?
So yeah, you can reduce it to spec of not a field, but like spec of a ring. So every quotient stack would look like, every algebraic stack or ANS stack would look like some affine mod G, where G is defined over some affine base scheme, and then this affine scheme is also over that. So it's basically a quotient stack over the affine scheme. So that's what we are reducing it to. Okay. So the idea is that reformulate and extend the result of Land-Tamme in categorical framework. Okay. And once we do that, the main theorem is the following categorical Milner excision statement. So it says the following. So let delta be a square of compactly generated presentable stable infinity category and colimit preserving functors between them. So E to B, E prime to B prime. I'm writing these as upper stars, but the point is because these are presentable stable infinity categories, and F upper star is supposed to be so because it's colimit preserving, then it would automatically have a right adjoint, and this upper star is supposed to indicate that it's the left adjoint of that functor. So Q of the star and P of the star. And now we want to reformulate the condition that we have from a Milner square of rings into what does it give us in terms of the categories. So the example to keep in mind is where these A, B, A prime, B prime are just the module categories over the rings that we had. So first, we want P of the star and F of the star, which goes from A to A prime cross B over B prime. This is fully faithful. And all our functors should be compact and generate their codomain under colimits. So all F of a star, G of a star, P, Q are all compact. So because we are working with compactly generated categories, this just means that these functors preserve compact objects. So are compact and generate codomain under colimits. So in the case of rings, these two properties together correspond to being Milner. So this is like Milner. And the fact that these generate under their codomain under colimits, this follows from the fact that you have a map of affine rings, and also that you're taking one of the map is actually surjective. Okay. And then the third independence condition can be reframed as some base change property. So if delta cat satisfies base change, base change. So that means the natural transformation, which is from, so P lower star would be the right adjoint of your P upper star. And then this map to Q lower star, G upper star, this should be an isomorphism. So once you have a square of categories which have these two properties, so this second property corresponds to third independence. Third independence. And once you have these properties, what you can show is K theory of such a square is Cartesian. And then K of delta is Cartesian. And the pro version of the categorical result looks as follows. So now we need more some subtle conditions on the generators. So if delta is a square of pro systems, along with all the properties that we had before, that is, they are all the categories are presentable, stable infinity categories, and functors are all colimit preserving. So that means I have some an, bn, a prime n, b prime n, and for each n you have such squares. So it's a diagram of such categories satisfying level-wise base change and level-wise Milner. So we'll call this as the square being having pro base change and pro Milner. So that means that you have an indexing for which it is level-wise satisfies base change, and also there is some indexing of your pro system for which it also is level-wise Milner. Although these two may not be the same, and this is why you need the following subtle assumption that and some technical generation assumptions. Which I want to roughly say as following. So the categories are uniformly projectively generated and the mapping spectra of these generators, the mapping spaces of these generators are uniformly bounded. Okay. So what I mean by this is the following, that there should, so okay, in the simplest case, there exists some set of compact projective generators for this AN, not exactly AN, but kind of the connective object. If you so if you're looking at module category, what you want is that the bounded to the right complexes are all generated by some set of compact projective generators. And you also need their mapping spaces between them to be uniformly bounded. So what that means is all their homotopy groups should uniformly vanish about some given C, say, or given N, it should all vanish. So the point is, once you have all these conditions, what you can do is your category would sit as some localization of some connective modules over some even ring. And then if you can, under all these conditions, you can actually show that some kind of pro-equivalence holds for that. And then this would give you a pro-equivalence for this O dot and this B prime itself. So all this comes in because you don't have base change and Milner for the same kind of indexing category. So you have to make sure that somehow the pro-equivalence of the O dot and B prime can still be achieved up to some level. And this is what this kind of projective generators would buy for you. Okay. Did I write? Okay, I didn't write the conclusion of the theorem. So the conclusion is, if you have all this, then K of delta is pro-Cartesian. So this is really some delta n. So this is pro-Cartesian, or just Cartesian because I'm in the pro category setting. Okay. And so in the special case of when your categories are just module category over some even rings, this would this is the result of Land-Tamme. So Land-Tamme is a special case where the categories are module categories over some even ring. Okay, so basically in the module category version, you had one generator, and now what we are saying is, as long as you have a good set of even a set of projective generators, then you can still prove a pro version of the Land-Tamme result. So now we want to use this to prove the Milner excision for algebraic stacks. So corollary is Milner excision for okay, so let delta be a square of Noetherian and ANS stacks. So by that, I mean the stack has affine diagonals and has nice stabilizers. For this particular result, you can also do with lesser by just having some linearly reductive stabilizers, but for the simplicity of notation, I just want to make this assumption. from the beginning. So ENS stacks, which is Cartesian and co-Cartesian. So so that means recall our square was as follows, where y to x was a affine morphism, and z was some closed substack of x, and then you had this pullback. So such squares of stacks are what are called Milner. So this is the definition of a Milner square of stacks. And then if the square is Tor independent, then K of delta would be Cartesian. And K of delta is always pro-Cartesian. So that means the square where you take K of z to K of y. So these are the constant pro systems, and what you have here are so these are closed substack of x. So you can form this in stack, which is the formal kind of the analog of formal stack or formal scheme. And then we are saying that if you take all these thickenings, then and take the pro-K theory spectrum corresponding to that, then this square is Cartesian. So this okay, that's Cartesian. Okay, and a remark is that the way this goes, all the categorical Milner equation statement also holds for any localizing invariant, just as in Land-Tamme. So also holds for other localizing invariants. Okay. Any questions? Okay, so now that we have this, what I want to do is sort of use this kind of thing to prove pro-cdh descent for stacks. Okay, so pro-cdh descent. So before going into that, let me recall what cdh squares are. So a proper cdh square, or also called an abstract blow-up square, of algebraic stacks, or also derived algebraic stacks, is a square of the following form. So it's a square delta, which is y to x, where f and some closed inside x, and this is the pullback, such that delta is Cartesian. In the case of derived stacks, you have to assume that only that it's Cartesian on the classical underlying stack, so on classical truncations. And F is a representable and proper morphism. This I is a closed immersion with quasi-compact open complement with quasi-compact complement. And this map is birational, that is, it's an isomorphism outside of this Z. So F is an isomorphism on the open complement. And it would be called a finite Cdh square if you have that F is also finite morphism. So delta is finite Cdh if F is not just proper but finite, if F is finite. Okay. And the Cdh topology for algebraic stacks is generated by taking these kind of proper Cdh squares along with Nesnevich squares. So Cdh topology is given by Nesnevich plus proper Cdh. Okay. And combined with the Nesnevich descent result, we want to show that we also have a proper Cdh descent, which would give you descent for the or pro-descent for K-theory of on the Cdh topology. So so first, what we'll do is, okay, so the Milner squares can only handle kind of closed immersions and affine morphisms. So we first do the finite Cdh square case, and then use this somehow to, along with the usual blow-up excision for blow-ups to show a proper excision for this proper Cdh squares. So the first result is that given a finite Cdh square, delta of bounded Noetherian. So this boundedness is really an assumption when you take derived stack. So so a derived stack would be bounded if it has a cover by some affine derived scheme which has bounded homotopy. So derived algebraic stack as above. So as above, this d of delta. So first, I want to say that if you have a finite Cdh square of algebraic stacks, and if you took the derived category of quasi-coherent sheaves on that, then it would satisfy the conditions of the categorical Milner excision that we had. And then we just apply that to say that you have a excision for pro-K theory if you apply it to this sort of derived categories somehow. Then this is pro-Milnor and satisfies pro-base change. And when X, your stack is really a quotient stack where G is some embeddable nice or maybe just linearly reductive group scheme over some affine, over affine scheme S, and X is affine over S and has a G action. G action. Then if you take the representation, so G is a linearly reductive group, so you can take the irreducible representations of G over S, and these would form basically the projective generators. So then vector bundles over BG form a set of compact projective generators. And also for all d of y, d of z, d of w, and so on, because all of them would be of the form affine mod the same linearly reductive group G. Okay, so this would imply that therefore K-theory satisfies pro-excision for finite Cdh squares of bounded derived Noetherian ANS stacks. So basically, you use first the local structure theorem to reduce it to affine mod linearly reductive. And then because of Nesnovic descent, you can actually do this. And then for this particular case, it would follow that you have all the projective generators and it is pro-Milnor and satisfies pro-base change. So therefore, you can show that K-theory has pro-excision for such squares. Okay, and now to get the proper CDH excision from this. So first, we prove the case where you don't have an arbitrary proper map, but in fact, this is given by some blow up. So you have actually a square where y2x is the blow up along this closed subscheme. Okay, so case of blow up. So this would follow from the following. So it's a result of Adeel from 2020, who he shows that K-theory satisfies excision for quasi-smooth blow-ups. So if you have an X and which is derived and we use some quasi-smooth closed embedding inside it. So quasi-smooth closed embeddings are just locally some zero locals of some vector bundle, some section of that. And then for such squares, K-theory has excision. So for quasi-smooth blow-ups. And now to get sort of the pro-excision for ordinary blow-ups, what we do is you take this blow-up square, and then if you have a blow-up square of classical stacks, you can always, up to some thickening, change it into a quasi-smooth blow-up square for some, so it's a blow-up square for some quasi-smooth derived closed subscheme. So you have some closed subscheme, you can thicken it such that it's a quasi-smooth immersion, and then show that if you take a blow-up along that, then that would have K-theory excision for K-theory by this result, and then you can also get a pro-excision result by combining it with the finite excision result now applied to just closed immersion. So the proposition is as follows. So for any blow-up square of Noetherian ANS stack with resolution property. So we have to also assume that the coherent sheaves are quotients of vector bundles, but locally you can always reduce to this case because locally it's just quotient stack. So so we just combine this with the Nesnovic descent again to get excision for all blow-ups, but in this form it's only true when it has resolution property along closed embedding. Then K-theory satisfies. So the proof that I'll tell you is going to be true with resolution property, and then you can remove that condition by invoking the local structure theorem. So satisfies pro-excision. So the idea is the following. So if you have y to x, some blow up along some closed embedding, and this is your exceptional divisor, so W, then what you can do is you can factor this via some Z prime, which is now quasi-smooth inside X, and take a derived blow up of X along the Z prime. So you have some Z tilde and X tilde. So this is a derived blow up square. And you have E over here, and this is a so your original blow up would sit as a closed embedding inside your derived blow up. So this is a finite Cdh square. And then as formal schemes, this W and P are just isomorphic, and your Z and Z prime are isomorphic, are pro-equivalent, that is. Okay. So then the proof is first use the excision for quasi-smooth blow-up along with finite pro-excision to show pro-excision for this square. So pro-excision for 1. And we already have pro-excision for these finite Cdh squares. So this would, finite pro-excision implies and the fact that these formal stacks are isomorphic would imply that their K theories are also isomorphic or pro-equivalent. So this would show prove the proposition. Okay. And now to prove the result for any abstract blow-up square and not just a blow-up square, you use the usual kind of classification argument. So if you have an abstract blow-up square, then you can always, so if your square was given by this y to x, you can always take a further proper covering of y such that if you take now the base change of the square, then that is a blow-up square. And this y to y, this y prime to y, the proper covering is also by some sequence of blow-ups. So the fact that you have blow-up for these kind of squares would excision for these kind of blow-up squares would tell you that you have excision for all abstract blow-up squares as well. Okay, so here K theory satisfies pro-excision for abstract blow-up squares. Of Noetherian ENS stacks. And the proof is basically read Reynolds-Grosvenor stratification for stacks plus the above proposition. Okay. Okay, so in the last 10 minutes, let me tell you how to get the vanishing for K theory from this. So vanishing of negative K groups. So the idea of this is just similar to the Kerz-Strunk-Tamme proof, but the only difference is that now you have to work Nisnavich locally and then make sure that everything somehow also can be worked out Nisnavich locally and then combine it with the pro-cdh descent to prove that some negative K groups vanish. So first, let me recall the result of Kerz-Strunk-Tamme. So this is the Weibel's conjecture for schemes. So Weibel's conjecture. So it says that for a Noetherian scheme of dimension D, of full dimension D, the negative K groups vanish below this dimension. So K minus I of X is 0 for all I greater than D. And the reason for this is for this conjecture itself is that if you have a regular stack or a regular scheme, then all its negative K groups always vanish. And the presence of a resolution of singularity or something like this would tell you that you can make all negative K groups to vanish up to some pullback to this resolution of singularity. And then combined with somehow the pro-cdh descent, you should be able to conclude that the negative, every class in the negative K group itself vanishes. So, a lemma. So in the absence of resolution of singularities, you have sort of a killing lemma, which tells you that you can still make every K group, every class in the negative K group vanish up to some sort of stratification. So this was true for schemes by Kerz-Strunk and then extended to stacks by Hoiva and Krishna using the flattification for stacks due to Reed. So for every negative K group class, so for every I, which is strictly positive, and some class in K minus I of X. So X has to be X reduced stack with resolution property. Then there exists a sequence of blowups X prime to X such that the pullback of this class is 0 and K minus I of this X prime gamma. Okay, and once you have this lemma, the proof of Weibel's conjecture is by the following strategy. So, so this is Kerz-Strunk-Tamme for schemes. So the idea is that first using Zariski descent or Zariski spectral sequence, so Zariski descent spectral sequence. You can reduce the problem to some local thing. So reduce to X equals some affine scheme. And for this, you'll also need the fact that the Zariski cohomological dimension is bounded by its Krull dimension. So it's equal to the Krull dimension. So that says that all these cohomologies would vanish about the dimension, and this is important for the sort of reducing to the local thing, that you want the higher cohomologies to vanish. And then you use pro-excision for blow-ups. So once you reduce to the affine case, then your schemes would have the resolution property. And also you can assume that they are reduced because the negative K group of schemes is nil invariant. So this would allow the killing lemma to be applied. And then you can show that from the Mayer-Vittorius exact sequence for blowups, you can show that if the class vanishes in just this K group of X prime gamma, it should also vanish by some induction hypothesis on K group of X itself. So this is pro-excision for blowups, plus some induction on dimension. And now when you want to do this for stack, the stacky case, the idea is similar. So we want to use some sort of now the Nisnavich distance spectral sequence to reduce to the case of just affine mod linearly reductive, so that then we have the resolution property, and we can also assume that it is reduced by result of VOVA, that the negative K groups somehow depend only on the weight hat, so it does not see this thickening. So and then you can conclude that you have also the Weibel's conjecture for stacks. So first, you have a Nisnavich descent spectral sequence which converges to KQ minus P of X. And we show that the cohomological dimension, the Nisnavich cohomological dimension, although we don't know that it's bounded by the Krull dimension, we can still show that it is bounded by something called the covering dimension of the stack. So plus Nisnavich cohomology is bounded by a covering dimension of the stack. So let me make this definition. So the covering dimension of an Euclidean stack. So basically, you take all coverings by schemes or algebraic spaces and take the minimal such dimension. So that's what the covering dimension is. So is the minimum n such that there exists FPPF cover from X to the stack, where X is a Euclidean scheme of dimension n. For Deligne-Mumford stacks, this covering dimension is same as the usual Krull dimension. But for Artin stacks, this is not true. So the covering dimension can be strictly larger than the Krull dimension. But we have to work with this dimension so that we have sort of the Nisnavich cohomology vanishing. And then I tell you that the negative K groups of such of quotient stacks where you have a affine mod G, where G is linearly reductive, is isomorphic to this whenever B is a nil extension of A. So for E to B, nil extension. And for all I greater than equal to 0. So this allows us to reduce to the case of reduced quotient stacks, and then we have the killing lemma, and we can combine this to prove the Weibel's conjecture. So let X be an Artesian ANS stack of covering dimension D. Then K minus I of X is 0 for all I strictly greater than D. Okay. Okay, I'll stop here. Yeah. Thank you.
Let's thank Charanya for this talk. So I got a very basic question. So many of the results are stated for Noetherian ANS stacks. Does that cover basically all the stacks that we possibly interested in, or are there some?
So at least in the quotient stack case, this would mean you can take things of the form some scheme mod, some torus or finite et al. Group schemes and such things. But in the general stacky case, I think you can allow still more or less all daily Mumford stacks. You just need some separated and tame assumption. But in the Artin stack case, so it's sort of a strong property, but in characteristic P, this just requires all your stabilizers to be linearly reductive, which is good, which is not such a strong thing to ask for. But in characteristic 0, you really have to make this stronger assumption. Like you cannot have something like GLN or something, but yeah, this whole assumption just comes from the fact that we want to use the local structure theorem such that it is a quotient stack, and this is somehow sort of restrictive. So maybe there's possibility of extending to more general stacks, but at least we don't know how to do that so far.
Right. Okay, thanks. Any other question? Just go ahead. No questions, no further questions. Last chance. No, it doesn't seem to be the case. So thanks again, Charanya, for a very nice and clear talk.
Thanks a lot for having me. Thank you.